Hi, and welcome to Unit 7, Day 1, Electrochemistry. In this unit, we're going to address two key questions. The first one, what are electrochemical reactions, and how are chemical and electrical energy interconverted during these processes? These reactions take place in what are called electrochemical cells, and there are two types, voltaic and electrolytic, and you'll learn about those later. The second key question is, what is the driving force, and how do we quantify the driving force behind electrochemical reactions? For this very first video, we're going to focus on the first key question. All right, so what is electrochemistry? It is the study of the chemical reaction that generates or uses electrical energy. And chemical reactions are also known as redox reactions. And this word comes from a combination of the words reduction and oxidation, which are the two processes that take place during a redox reaction. The reduction reaction is a reaction that gains electrons, and the oxidation is a reaction that loses electrons. So the electrons that are lost by the oxidation are gained by the reduction. It causes a flow of electrons or electrical current. Let's look at an example of reduction reaction. If we have a copper 2 plus ion and we add 2 electrons to it, it will form a neutral copper solid, which would be an example of reduction because we're gaining electrons during this process. An example of oxidation would be a zinc neutral solid that will lose electrons to generate the zinc 2 plus ion and 2 electrons. To get the overall reaction, we can simply use Hess's law to sort of combine these two reactions. And remember, with Hess's law, what's ever found on both sides of the arrow, when you add them together, will cancel out. So in this case, it will be the 2 electrons, they will cancel out. And so you don't see those in our overall reaction. However, what you do see are the two reactants of the reduction and oxidation reaction, so the copper 2 plus and the zinc solid, those will be our reactants, and our products are the copper solid and the zinc 2 plus. In this unit, you're going to have a lot of terms to memorize, and the first terms are reduction and oxidation, so you definitely want to find ways of memorizing them. As much as I can, I'll try and give you some tricks. So here are a couple of tricks for memorizing reduction and oxidation. You can choose one, both of these to memorize, if it's helpful for you. So the first one is Leo the line goes Gur. If you memorize this expression, it will help you to know when you're dealing with oxidation and reduction, are you losing or gaining electrons? So for the Leo the line goes Gur, the Le stands for loss or lose electrons, and when you lose electrons, it's oxidation, and the Gur stands for gain of electrons is reduction. The other example is oil rig. It's similar, so the O is for oxidation and IL is loss, so loss of electron. So oil is oxidation is loss of electrons, and rig is reduction is gain, and the gain being of electrons. As I said, you can memorize one or both of these, and if you do, then you will have no problem memorizing when you're dealing with reduction, are you gaining or losing electrons? When you're dealing with oxidation, are you gaining or losing electrons? These mnemonics will be sure to help. Okay, before we go any further, sorry about that, we want to talk about why it's important real quick, because why are we studying this in the first place? Electrochemical studies are important for developing better batteries. Here we have on the left one of the oldest or first batteries that were ever built and constructed. These batteries weren't very powerful, they weren't very safe, and they weren't rechargeable in the way that we recharge our batteries today. So as a result, scientists have studied ways to make better batteries, and so now you have batteries that are portable and can fit into your phone and can be recharged, and you have these very powerful batteries that can be used to power a car like this Tesla car here. Another example, if you're into jewelry or metalworking, is electroplating. This is a very common example where you can deposit a layer of metal, usually onto the surface of another metal, using electrochemistry. And so here's an example of a piece of jewelry, or also very common with silverware and silver pots and pans is copper plating. Copper, I believe, is a better conductor of heat, and it's also more durable and resistant than the silver. All right, so going back to electrochemical cells. As I said before, electrochemical reactions take place in electrochemical cells. And we're going to look at what those look like in a moment, but first, why do they take place there? Why do they need to take place there? It's because the oxidation and reduction reaction must be kept separate. So if they're not kept separate, then the electrons will just recombine and then the reaction will just stop. And if it stops, you won't be able to generate electricity if you want to generate electricity, or you can't really pump enough in order for it to go. So when we talk about voltaic or galvanic cells and electrolytic cells, those are the two types of electrochemical cells. And the only difference between them is one spontaneous and the other one is not. So in the voltaic or galvanic cell, the redox reaction is spontaneous. And that means that it's going to generate electrical energy for you. So if you have a voltaic or galvanic cell and you hook it up to a light bulb, you can light your light bulb. On the flip side, for electrolytical cell, it's a non-spontaneous process, and so the system has to gain electrical energy, meaning you have to pump that electrical energy in order to make that reaction go. Now, it's important to know which cell you're dealing with, because things like, as you can see here, the signs of the anodes and cathodes, which we'll learn what those are later, are different. And also the cell potential sign is also different based on whether you have a voltaic or electrolytic cell. All right, let's move into the parts of an electrochemical cell. It's important to know what electrochemical cell is composed of, so you can have a better idea of what's happening. So there are four main parts. You have the electrodes, you have some sort of voltmeter, which measures your cell potential, you have a salt bridge, and you have a wire connecting the electrodes. We're going to start by zooming in on the electrodes, the anodes, and the cathodes, and see what's happening here. So let's begin with the anode. At the anode is where the oxidation reaction takes place, and you have to know what that word means and what reaction takes place there. No matter what electrochemical cell you have, oxidation is going to take place. And if we look at the example with the zinc solid forming zinc ions, where oxidation meaning we're losing electrons, that's the chemical reaction that's happening. So zooming in on a close-up, we have this piece of zinc metal inside of a solution of zinc nitrate. And the zinc nitrate will generate the zinc ions. When you dissolve zinc nitrate, it generates zinc ions. And what happens is the zinc anode, the zinc metal, will pump electrons into, pump zinc ions into the solution as it is losing electrons. So if you take a close-up of the surface of the anode, you will see that here we have these green spheres. The big green spheres, they represent the zinc metal. And as the reaction is going on, they will start to become zinc cations. On the flip side, at the cathode, what's happening is the reduction. So anode is oxidation, cathode is reduction. And if you take a close look, what's happening here? In this case, the copper ions, which are found in the beaker, so you have a solution of copper nitrate here, those ions are combining with electrons, and that forms this neutral copper, which will start to deposit onto the surface of the metal, the copper metal, or the copper electrode. And so that will be a close-up here. So key things to remember is anode, you have your oxidation, cathode, you have your reduction. And in order for these processes to work, you have to have the piece of metal inside a solution with the metal ion. So you have to know anode and cathode, and a quick trick for memorizing that is red cat and ox. So reduction takes place at the cathode, oxidation takes place at the anode. So reduction, cathode, anode, oxidation. I just want to briefly mention that this is true for both voltaic and electrolytic cells, where the reduction takes place at the cathode and oxidation takes place at the anode. The only difference between the two cells is the cell potential are different, have different signs, and the sign of the anode and cathode are different for voltaic. So for voltaic, the anode is negative and cathode is positive. And electrolytic, the anode is positive and the cathode is negative. And I think sometimes people, if you've had physics, you may have seen this case, and so you're not so sure which one it is. But so it depends on what type of cell you have, voltaic or electrolytic, in terms of the sign. But no matter what, anode is oxidation, cathode is reduction. And memorizing this mnemonic will help you. Okay, there are a couple more parts I want to talk about for electrochemical cells. So we've already looked at the electrodes. Let's talk about the wires next. So as you notice here in this diagram, you have wires that are connecting the two pieces of metal, the two electrodes there. And it's through these wires that the electrons flow. So the electrons flow through here and they can be monitored through this voltmeter. The final thing, which is super important, is the salt bridge. It sort of just acts to maintain the charge balance in the solutions, because what's happening here in the case at the anode, we are building up of zinc 2+ ions, because they're being the zinc is being removed from the metal plating and forming these ions. So we're building up this positive charge inside the solution. If you build up too much positive charge, the reaction is just going to stop. So to sort of maintain that, what happens is the salt bridge, which is made up of some sort of inert salt like NaCl, and all salts have a cation and an anion. The anion part, which will be the Cl-, will start to pump through into the solution to sort of maintain that charge balance. So the buildup of positive charge here is sort of balanced out by the addition of negative charge. On the flip side, for our cathode here, the copper 2+ ions are being removed from the solution and they're depositing onto the copper plate. So to sort of replace that, the cation in our salt bridge, in this case NaCl, will start to pump into the solution to sort of build up that positive charge, or help reestablish that positive charge to maintain a neutral solution here. So the solution here should be neutral. It shouldn't have a bunch of positive charge, shouldn't have a bunch of negative charge, or the reaction will stop. So that's the purpose of the salt bridge. You may be asked to determine the flow of, or the sign, the flow of the cations and anions from the salt bridge. So it's important to note that at the anode, the anion of the salt will flow into the solution, and at the cathode, the cation of the salt will flow into the solution. I just want to point out there are different types of salt bridges, just in case you see them. There's this sort of U-shaped salt bridge, which we've seen previously, but you also may see one where the two beakers are connected with what's called a porous disc, and that is the two solutions sort of can flow in between both. That's just so that if you see it, you can recognize it. The salt bridge should be distinct from the wire, because the wire will usually be just shown as this sort of like black line that are directly attached to the electrodes. You see the electrodes attached to them there. All right, before we end this video, you have one quick CFU. You're going to label the electrodes as anodes or cathodes and explain how you label them, and then also draw the path for the movement of electrons. And I don't know if I pointed that out, but it's important to note that the electrons will always flow from anode to the cathode, no matter what kind of cell that you have. So once you've identified what your anode is and what your cathode is, you can draw the path flowing in that direction. All right, take a moment to try the CFU and press pause. When you press play again, you will see the answer. Okay, so here's the answer. So if you look at the reaction at the base here, that is the an oxidation reaction. We know that because we're losing electron. And since it's an oxidation reaction, that makes it the anode. On the other side here, we have silver ion. We're adding on an electron, so we're gaining electron. That means it's reduction, and that means it takes place, that this side would be our cathode. So basically what you would need to do is you need to look at the reaction, figure out if you're losing or gaining electrons to determine if it's oxidation or reduction. Once you know that, you will know if it's the anode or the cathode. Finally, once we know what our anode is, we can draw the path of electron flow from the anode to the cathode. I hope you found this video helpful.